Hi guys, we're continuing titrations and we are looking at titration between a weak acid and a strong base. So the weak acid we're using is acetic acid, CH3COOH. Our strong base that we're using is NaOH. We're using 10th molar of each, and we're going to start with 40 milliliters of the acetic acid in our flask, and then with the burette we're going to slowly add the NaOH. So we first want to know the pH before any NaOH is added. So just our weak acid is in our flask. So here's our flask. We only have the CH3COOH and it's 10th molar. So since it's only a weak acid that is there, the way that we find the pH of a weak acid is by writing the dissociation equation for the weak acid and doing an ice chart. So let's do that. We have CH3COOH. It only partially ionizes into H+ and the acetate ion because it's weak. We're going to do an ice chart, and we're going to say initially it's 10th molar. We don't have any of these. Some of it is going to ionize, so it's going to get used up. Some of the H+ and acetates will form. So this is 0.1 minus X, X, and X. Then we're going to write our Ka expression. It is the concentration of the H+ times the concentration of the acetate ion over the concentration of my acetic acid. Ka for acetic acid, you look that up, it is 1.8 times 10 to the negative fifth. So that's equal to X times X over 0.1 minus X. X here is the H+ concentration at equilibrium, and it turns out to be 0.00133 molar, and so the pH is negative log of that, which ends up being 2.88. And so that is our initial pH just in our flask with only our acetic acid. So now we're going to open up our burette and we're going to let out 10 milliliters of 10th molar NaOH. So when you are doing a titration, so you're adding an acid and a base together, what you do first, if you're trying to find the pH or really anything about the titration, what you want to do first is look at the reaction between the acid and the base and write out the equation. And acids and bases, when they react together, that goes to completion. So you write one arrow, and because it goes to completion, we don't do an ice chart, we do a Bca chart, a Bca table, before, change, and after. And what you want to do is use your moles and look at which one's your limiting reactant, what gets used up, what's left over, and then once you figure out what's left over, you figure out how to find the pH based on what type of substance is left over. So let's do that. So we have NaOH, which is a strong base. Remember, if it's a strong base, we can write it as just OH minus. If it's a strong acid, we can write it as just H+, because the other ions would just be spectators. If it's weak, whether it's an acid or a base, then we have to write its whole formula. So we're going to take our base, OH minus, and we're going to react it with our acid. And again, this goes to completion when you have an acid with a base. And you're going to form water and then also some acetate ion. Okay, and we're doing our Bca table. And we usually do our Bca table in moles. So we need to figure out the moles. So we have 40 milliliters of 10th molar acetic acid, so that's 0.04 liters. Times 0.1 moles per liter. That gives us 0.004 moles of my acetic acid. So I'll put that here, 0.004 moles. For my base, I have 10 milliliters, so 0.01 liters, and it's 10th molar. And so that gives me 0.001 moles. So I'm going to put that here, 0.001 moles. So when you're doing the Bca table, of course, we don't have any acetate. We don't care about the water. When you're doing Bca table and you're doing it in moles, because this is a reaction that goes to completion, that means there's a limiting reactant, there's an excess reactant. So you want to figure out what is your limiting reactant. They are a 1-to-1 ratio, and you have 0.001 moles here, 0.004 moles here, so that means my hydroxide is my limiting reactant. So that gets used up. So my change is negative or minus 0.001 moles because my hydroxide is my limiting reactant, so that means it all gets used up. So because it's a 1-to-1 ratio, I'm going to use up the same amount of my acid, and I'm going to form the same amount of my acetate. So after the reaction is done, I don't have any more hydroxide, no more NaOH, it's all used up. I do have some leftover acetic acid, and now I have formed some acetate ion. When you're done with your Bca table, you might want to divide by the total volume so that you can get molarity, because eventually we're going to use molarity to find the pH. So I'm going to go ahead and do that. So I have 10 milliliters of the NaOH, 40 milliliters of the acetic acid in my flask here, and so together they make up 50 milliliters of solution. So I'm going to divide by 0.05 liters. This gives you 0.02 molar, and this gives us 0.06 molar. Okay, so when you have added your acid and your base together, they react together, you do your Bca table, you figure out, oh, what you're left with is some acetic acid and acetate. That's all that's left in your flask after the reaction happens. So this is a weak acid, and this is its conjugate. So guess what? We made a buffer. And that's why at the beginning of a titration, when you're adding just little NaOH, you have this pH here going up very, very, very slowly. This is called the buffering region, the acidic buffering region, because what you do is you basically form a buffer because you have your weak acid and you form some of its salt. And so it behaves like a buffer, and that's why it goes really, really slow. So we're left with a buffer. We're left with a weak acid and its conjugate. How do you find the pH for a weak acid with its conjugate or of a buffer? Well, you have two options. You can write the dissociation equation for your acid like this and plug in your molarities for the acetic acid and the acetate, do a Ka with your ice chart. Or you can also use the Henderson-Hasselbalch. And so I'm going to use the Henderson-Hasselbalch because it's just a little bit shorter and easier. So I'm going to say pH is equal to pKa plus log of my conjugate base over my acid. So pKa is negative log of the Ka, so negative log of 1.8 times 10 to the negative fifth, plus log of my conjugate base is my acetate. I have 0.02 molar. My acid is 0.06 molar. It's my acetic acid. And I calculate that, and this gives me 4.27 for my pH. So I'd like to show you a representation of this here. So we have in our flask right now 40 milliliters of 10th molar acetic acid, which is equivalent to 0.004 moles. So each of these is going to be 0.001 moles. So I have 4 of them. Acetic acid is a weak acid, so most of it stays molecular, very little of it ionizes, and so that's why I have it represented kind of stuck together or bonded together here because it is molecular. And then in my burette, I have 10th molar NaOH. And I'm going to start by adding, opening up my burette and adding only 10 milliliters of the NaOH. So 10 milliliters is equivalent to 0.001 moles. And so I'm going to just release just one of these formula units. So I'm going to go ahead and do that. And you see that my NaOH reacted and the hydroxide combined with the H pluses from the acetic acid to form water. And then I formed acetate ion, just like we saw with our calculations. I do have some sodium ions that are just floating around. They don't really affect anything. So at the end, when I'm done in my flask, of course I have some water. I have some sodium ions. I have some acetic acid still left. See, those 3 are all acetic acid. And I also have some acetate ion. So looking at all of these things, the sodium ions and the water, of course, are neutral, so they don't affect my pH. But I do have acetate ion and acetic acid. Those do affect my pH. And so what I'm left with is a weak acid with its conjugate. And so to determine the pH, I use either the Henderson-Hasselbalch equation or I do the dissociation of the weak acid with an ice chart. Okay, let's look at the next one. So now, instead of 10 milliliters of NaOH, I'm going to add 20 milliliters of NaOH. So in my flask, I have my acetic acid, and I'm going to add 20 milliliters of NaOH. I have an acid, I'm adding a base to it, so I'm going to write out my reaction. And so NaOH, I'm going to use OH minus, like we did before, so we're consistent, plus the acetic acid. One arrow, I'm going to form water and acetate. So same reaction, of course, because we're using the same reactants. I'm going to do a Bca table because I have an acid and a base, so it goes to completion. So our acid is not going to change. I still have 0.004 moles because I had my 40 mils of the 10th molar right here still, right? But my base, now I have 20 mils of 10th molar. So 0.02 liters times 0.1 moles per liter. That gives me 0.002 moles. So this is 0.002 moles. Don't care about my water. This is 0. Which one is your limiting reactant here? Which one will run out first? That's going to be the hydroxide. You have less of it, and it's the same molar ratio, moles, 1-to-1 ratio. And so this is my limiting reactant. So I'm going to use it all up. I'm going to use the same amount of my acid, and I'm going to form the same amount of my acetate. So at the end of the reaction, I don't have any more base left. I do have some of the acetic acid, and I have formed some of my acetate. So let's go ahead and divide by the total volume. I have 40 mils of the acid and 20 mils of the base, so that's 60 mils total, so 0.06 liters. So that's a third. This gives you 0.0333 molar for both. Oops. So 3 there. Okay, so what I'm left with is, again, a buffer, right? I don't have any more of my base, but I do have a weak acid and its conjugate. So that's a buffer again. So to find the pH, you could do the Henderson-Hasselbalch or the dissociation equation of your weak acid and do an ice chart. But this is special because you notice that the molarity of the acid is the same as the molarity of the conjugate base, right? And so what does that mean? Do you remember? This means you're at half neutralization point. Half neutralization point. What does that mean? That means you've added half of the amount of the base that you need to get to the equivalence point. You added half of the amount of base that you need to use up all your acid, right? So if this is my equivalence point and it requires, let's say, this is not correct, this graph here, it should be 40 mils that we would need. We've added 20 mils. So we are half neutralized, which means the pH is going to equal to my pKa. Here's why. Let's say you do the Henderson-Hasselbalch. So if you were to plug in your numbers, you'll see that the conjugate base and the acid are both the same concentration. And so the same number over itself is equal to 1. Log of 1 is 0. And so pH would be equal to pKa plus 0, which is the pKa. So when you're at half the neutralization point, your pH is just equal to your pKa. So in this case, it is equal to negative log of 1.8 times 10 to the negative fifth, which is 4.74. So that's our pH at half the equivalence point. Let's look at our animation for this one. So now I'm going to add the 20 milliliters. And so I have the same amount. There's my 4 particles to represent the 0.004 moles. And now I'm going to add 0.002 moles of the NaOH. So that means I'm going to add 2 of these NaOHs. So here's the first one, and then here's the second one. So what are we left with? Well, same stuff as before. We have some water. We have some Na pluses. We have some acetic acid, and then we have some acetate. So we have a weak acid and its conjugate. But this is special because we have the same amount of acetic acid as we do the conjugate. And so this is half the neutralization point or half the equivalence point. So the pH is equal to the pKa. And so if we've used 20 milliliters to get to half the neutralization point, that means that we'd need double that to get to the equivalence point. So if we use 40 milliliters of NaOH, we know that we would reach the equivalence point. So let's look at the next one. Now we're going to add the 40 milliliters, so we're at the equivalence point. So as always, when we have a titration, we have an acid and a base. We're going to write our equation. And it's a one-way arrow. We form water and acetic acid again, or sorry, acetate ion again. We're going to do our Bca table. So this is still 0.004 moles. I automatically know, because we just talked about the equivalence point, that the hydroxide is also going to be 0.004 moles, right? Because it's the equivalence point. They have to both match. But just to show you the calculation, you have 40 mils, so 0.04 liters times 0.1 moles per liter. And so that gives you 0.004 moles. That's where we got that from. Don't care about the water. Here we don't have any to start with before our titration. So if you look at this, because it's a 1-to-1 ratio and we have equivalent number of moles, that means we don't have a limiting reactant. They both get used up, right? So we use up 0.004 moles here. Same thing here. And we form 0.004 moles here. At the end of my reaction, I don't have any more of the NaOH. None of the base is left. None of the acid is left, but I do have some acetate ion left. We're going to divide by the total volume so that we can get the molarity. We have 40 mils of acid, 40 mils of base, so 80 mils total, so 0.08 liters. And so that gives us 0.05 molar. Okay, so we've reacted our acid and base, looked at what's left. Look at that. We don't have any more of this. All we have is acetate ion. So how do you find the pH for just an acetate ion? Well, remember, acetate ion is not neutral. It can undergo hydrolysis, right? So we are going to write the hydrolysis equation, do an ice chart for that, and then find the pH using that. So let's try it. So my acetate ion, I'm going to do it here, is going to react with the water. Now this is hydrolysis, so that's going to be a two-way arrow. That's an equilibrium. And we're going to form some acetic acid and some hydroxide ions. And that's why it's not neutral, because it's forming some hydroxide ions. This is an ice chart because it's an equilibrium. Initially, this is 0.05 molar. Don't care about the water. 0 and 0 minus x plus x, 0.05 minus x, x, and x. Now watch out, because this is basic, we got to use the Kb expression, not the Ka. So Kb is going to be concentration of the acetic acid times the OH minus over the acetate ion. Kb for acetate, you can look it up, or you know the Ka for acetic acid, so you do Ka times Kb is equal to Kw to solve for Kb. But Kb ends up being, I believe, 5.6 times 10 to the negative 10th. That is equal to x times x over 0.05 minus x. X is not the OH minus, that is not the H plus, it's the OH minus, right? So that is the OH minus concentration. And it ends up being 5.29 times 10 to the negative 6 molar. So POH is negative log of that, which is 5.28. And so my pH is going to be equal to 8.72. And that's the pH at the equivalence point. This is a weak acid with a strong base, so it should make sense that the pH at the equivalence point is higher than 7. And so that would be right here. Remember, the equivalence point is where you halfway between the two inflection points. So where you see the line curving there, and so halfway between, that's your equivalence point. Let's look at our animation for this one. So we are going to look at now adding 40 milliliters of NaOH. So here are my 0.004 moles of my acetic acid, and where I'm going to let 4 of these go down. So here's the first one, second one, third one, and fourth one. And look at that. So all of my acid and base are used up. So I just have some water, some sodium ions, and some acetate ions left. And so water and Na pluses are neutral, of course. They don't affect the pH. And the only thing that affects the pH there that's left in my flask is the acetate ion. So that's what determines the pH. And so you do the hydrolysis equation and an ice chart and get the pH from that, and it's going to be over 7 because the acetate ion undergoes hydrolysis and gives off OH minuses. So finally, we just want to look here at our graph here. So some key points on here is the initial pH before we start. The pH at half the neutralization point is equal to the pKa. The pH at the equivalence point, that's when your moles of acid and moles of base are equal to each other. That is going to be higher than 7 here because we have a strong base with a weak acid. And then finally, the ending pH is going to keep approaching the pH of just the base, which would be, in this case, close to 13, since it's 10th molar NaOH. Real quick, I want to point out the difference between half the neutralization point versus the neutralization point, what's equal here. So at half the neutralization point, your acid, your weak acid, and its conjugate are equal to each other. At the equivalence point, your acid and your base, like your reactants, are what are equal to each other.